Here's my tutorial for the 3.3 Fakie. Let's just talk about a fictional setup right here. I have magnesium with some anion, we'll just call it A. If it dissolves, remember it's a solid, right? Then I get Mg plus 2 and A minus 2. Now, if I dump some acid into this situation, I'm adding H plus, and of course it's not going to stick to the positive, it's going to maybe stick to the negative. So the question is, does it? Well, we can write it out like that, but the question is, will it really stick? And the answer is yes, it will really stick if you're not making a strong acid. So let's say it does stick, in which case this amount is going down because it's converting into that. It has less and less chance of reuniting one of these with one of those to remake the solid, because we keep removing it by putting it in there, by sticking it onto the H's. We've done the Le Chatelier principle stressing a system idea. By removing some of this, it makes the system shift right, and therefore the molar solubility will go up because we're making this the weak side and everything will shift right. The real question here is, will it stick? Because if we say that this is Cl, 2Cl, and then that's 2Cl, and then we're making HCl, the reality is we can write this on paper, but you're making a strong acid in water, which is not possible. You can't actually stick these two together. Now, you need your strong acid list, and it's on the board. So if you're trying to make a strong acid, the answer is no, you can't. You can't stick these two together. The whole point of a strong acid is that the H's immediately come off in water. They're extremely unsticky, so when you try to stick them back on here, it's not going to actually happen. So that's why this is not going to be affected, because you're trying to stick H plus onto Cl minus, and it can't be done. You're making a strong acid. Will H plus stick to S minus 2? Yeah, some, because H2S is not on your strong acid list. Will it stick to CO3? Very much. In fact, I made a big speech about how you get that when you stick H's onto CO3, and that even wants to become that, which is two of the most stable preferred products in the world. There's water all over the place and CO2 all over the place, and they don't sit around just reacting with stuff. They're very stable. Nature likes to make stable things that release energy. And before somebody can go and say, no, those are the reactants for photosynthesis, they are. But that didn't just sit around and happen. That took a very specific process that took a lot of evolution and is very dedicated to just doing that, and needs sunlight to power it for these to go back and get torn up and rearranged and turn into sugars. They don't just sit around and do stuff. So do the H's stick to that? Yes. Will this dissolve more and more as the CO3 gets removed? Yes. Will H's stick to OH? Come on, that's water. Of course they will. Will they stick to NO2? Now, that's not NO3, so yes, they will some. Will they stick to I? No, because then you're trying to make HI, and that is a strong acid, and it won't actually happen. Number 2, we have a fictional salt, AB2. It's a solid, and it dissolves into these. So the KSP would be this to the first times 2s. Remember, this is going to be double that one, 2s, and remember, it's to the power of the number in front. This, for like the 19th time, turns into 4s cubed. We don't know what S is. What are we finding? The molar solubility. What is the... Well, we're finding A plus 2 molarity. That also happens to be the value of S. So I get to ask, what's the molar solubility? What's that and the molar solubility? It's the same number in this case, isn't it? S is always the molar solubility. That might be a note to self, although I did say that before. S is the molar solubility, this S. So we know K, we know 4s cubed, divide by 4, take the cube root, and we got S. So did we find A plus 2 molarity? Yes, because this is the value of that molarity. It's also the molar solubility. It's how much of this you can dissolve per liter. It's the moles per liter. You can dissolve this. If you dissolve one of these, you get one of those, and two of that. If you dissolve 10 of these, you get 10 of that and 20 of those. Now, let's dose this ahead of time with 0.6 molarity of NAB. We know the NA's come off, so let's just do this mentally, and the NAs aren't going to affect anything. So how much A plus 2 do we have? None. And we have 0.6 of the B minus. We're going to add S of this and 2S of that, which means this is what we have at equilibrium. So this goes here, and remember it's squared. Now, to get us out of using the quadratic formula, we can just cross this out. If the K being used is 3 decimals or greater away from, smaller than, the molarity being used, then adding this in won't matter enough to take all the time and trouble to use the quadratic formula. And this is E-1, and that is E-7, so we're way beyond it. Scratching this out won't make any difference. So I scratched it out and I got this. I squared that and I got this. I divided and I got that. That is S. That is also the A plus 2 molarity, and it is the molar solubility. So does the molar solubility get affected by adding the solid? It does what? This number is a good bit smaller than that. In fact, it's over 1,000 times smaller. So yeah, adding a common ion first lowers the molar solubility. Number 3, we want to know if there will be a precipitate. That means we need to compare Q to KSP. What do we need for Q? We need the molarities of the ions. So let's write out the equation for the dissolving of the solid and make sure that we put a 2 there because there were 2 chloride ions that will come out. So what are the molarities? Well, we know the molarity and the liters of the Cl minus and the molarity and the liters of the PB. Now we're going to cross out the NO3 because that's a super soluble and it won't matter. It won't stick to anything in the water, and also for the Na. That's why we're just going to talk about the PB and the Cl. It's the only possible precipitate that there could be is one of these and 2 of that. Now, it's tempting to say that we will double whatever the Cl minus molarity is, but that's not true because we're going to only add an aqueous and an aqueous. These ions are not actually coming from this solid. Not actually. They're actually coming from the beakers that we're pouring together. But we write this out to remind ourselves of how we will calculate the Q math, that this will be to the first power and this one will be to the second power. But don't double this because it's not true that there will be 2 of these for every one of those, because we could add anything we want. We could add 9 of this and 100 of that and 2 of this and 19 of that. It doesn't have to be in a 1-to-2 proportion because they're not coming from the solid. So what are the molarities? Well, molarity times liters is moles divided by the new liters, because it's 50 milliliters and 80 milliliters is 130 milliliters. Now, also, you could just put 50 milliliters and 130 milliliters here, and it would cancel out, and you would get the same answer. So it doesn't super matter. But we get 0.308 for the Cl minus. We do the same thing over here, and we get 0.185 here. That goes in here and is to the first power. That goes in here and is to the second power. Then we square this, multiply here, and Q happens to be bigger than the KSP. So you've tried to drive Q up here past the KSP, which is not possible. This would be possible below KSP, but above is not. And so this amount that is part of Q being above KSP will not actually dissolve, and it will actually be the precipitate. On double I, notice we have a saturated solution. So we presumably have a little solid in there. So we can say that there will be some solid attempting to dissolve, in which case we would get S and 2S. However, it also is preloaded with 0.45 moles of NaCl in 2 liters. Notice 2 liters, which is why this value is half of that one, because the molarity is the moles divided by the 2 liters. So it's been loaded with 0.225 molarity of Cl minus. Sorry, this is where we got the Cl minus, of course, right? So this will be dissolving a little bit, making S and 2S, and this came in from the NaCl, which means these are the equilibrium values, and K is equal to then S times to the first times this all squared. 2S is going to be too small to be bothered with. Let's scratch it out. This squared is that times S, and divided under gives me that's S, and that is the Pb plus 2 molarity, because remember, this is S. So here we have a situation where we have NaCl is slowly added to a beaker. We know that Na won't stick to anything, so we can mentally cross that out. So effectively, we're just adding Cl minus to the beaker for our purposes of making a precipitate. So we have two possible precipitates because we have two cations. We have Ag plus, we're going to cross out the NO3 as immaterial because it's a super soluble and won't stick to anything. And again here, so we have this could stick to chloride or this could stick to chloride, but which one will stick first? Well, that depends on which one is stickier to chloride. Which one needs less as we add in the chloride? So let's write this out as a solid dissolving, even though that's not actually happening. And I really need to make that point. There is no solid dissolving, and it's confusing, and I have done it wrong myself. But we are adding the beaker of NaCl to these, which were already in there as aqueous. So there's no solids dissolving. We just want to write this out as the solid dissolving, just so we can see the math. So it does not mean that there's one of these for every one of those, because it didn't actually come from the solid. But we know that we've added this molarity of Ag plus. And the math is this to the first times that to the first will equal KSP, which I got from there. Which I got from back up there. So then we divide and we get the Cl minus molarity that would be necessary to cause K to be true. What happens when K is true? Equilibrium is established and a precipitate will form. This is the amount of chloride ion that is needed for a precipitate to form. We're going to do the same thing down here and write this out as the solid dissolving, even though there is no solid, just so we can see the math, that it's this molarity to the first times that molarity to the second. And don't say that there's 2 for 1, because this is not actually coming from the solid. I got this from there. But the chloride ion would need to be squared to make K be true. So what is K? I got it from back up top, and I set it equal to this. I divide and square root, and this is the chloride ion molarity that would need to be true to make K be true and make a precipitate form. Now, obviously, as we add the NaCl, it's coming up from 0. The molarity of Cl minus cannot be anything greater than 0 when there's nothing there. So it's got to rise from 0, and it's got to hit the smaller number first. And this is the smaller number. So AgCl solid forms first because it takes less Cl minus to form that solid.